Hello everyone, my name is Nikola Rankov and I work as a researcher at University of Bath. I will be presenting a talk called Simulation of Transionospheric Propagation over Yacamarca, Peru. This talk will show the initial development of a single propagation model experiencing equatorial scintillation. The equatorial ionosphere can have significant effect on radio propagation due to its complex behavior. Disturbances such as the equatorial anomaly and rising ionospheric plasma bubbles can significantly change the ionospheric conditions and thus distort the propagating signal. One such severe distortion is ionospheric scintillation. Scintillation is the random amplitude and phase fluctuations of a radio signal driven by rapid changes in the refractive index of the ionosphere. These sub-kilometer irregularities can cause refraction and diffraction of the incident radio waves, disrupting systems in RF communications, remote sensing, and navigation. In order to keep these systems operational, such irregularities have to be accurately modeled. This research tries to answer a simple question. Can a reliable model be built that will be able to simulate the changes to a RF signal propagating through an ionospheric irregularity? Any such model will require two parts, a model of the irregularity itself and a model of the propagation. The development stage of the model will address GNSS satellite-to-ground propagation transmitting on the L1 frequency band over the Yacamarca region in Peru. The accuracy of the model will then be evaluated using real data from the scintillation receivers from the Yacamarca Observatory. The diagram seen on this slide shows the workflow of the simulation during the development stage. The core of the simulation is achieved by implementing phase screen theory with a 2D split-step algorithm. The irregularity is simulated according to the power law spectrum models that have been documented extensively in previous research. Real DTEC data from GPS satellites and scintillation receivers in Yacamarca will be assimilated into the irregularity model. Calibration will then be achieved by comparing the amplitude scintillation index S4, calculated at the end of the simulation, with real S4 values obtained from the receivers in Yacamarca. The main motivation behind this research is to develop and calibrate a transionospheric propagation model that will be able to predict the behavior of radio signals operating on different frequency bands, used in various communication systems at low latitudes. Developing reliable and transferable models that can be implemented universally in different ionospheric conditions and in different communication systems is still a difficult task. As stated previously, the simulation of a scintillating GPS signal has two main parts: a model of the irregular medium that causes the scintillation, and a model of the actual propagation of the signal between the transmitter and the receiver. The irregularity is formed on the basis of the power law spectral model of turbulence. This is an established approach in the field of ionospheric scintillation that gives the ability to control the power of the irregularities according to their special scales. The current research uses the following derivation of the spectral model, where delta n is the power associated with different irregularity scales, gamma is the spectral slope of the model, and k0 is the wave number associated with the outer scale I0. It must be noted that the current model is built on zero-centered spectrum, meaning that the high frequencies of the 2D spectrum, kx and ky, are at the edges. The spectral model is then transformed into a special domain using the inverse Fourier transform. The epsilon k, seen in the phasor part of the equation, is a statistically independent 2D random variable between 0 and 1. This simulates the noise-like nature of the irregularity. It must be noted that the current model simulates an irregularity in total electron content, hence the final dimensions are electrons per meter squared. The following slide shows an example of the irregularity model in the spectral and special domain as a visual aid for the remainder of the talk. The graph on the bottom right side is the zero-centered spectral model, and the top left is its realization in the special domain. Recalling the three main parameters from the irregularity model in the previous slide, more precisely the irregularity strength delta n, the outer scale I0, and the spectral index gamma, can be seen affecting the shape of the spectral model on the bottom graph. The outer scale and the spectral index control the diameter and the slope of the bell curve in the center of the graph, and the irregularity strength, its height. This particular graph has been created by setting delta n to 5.6 times 10 to the power of 15, the spectral index to 3, and the outer scales to 500 meters. The grid of the resulting phase screen shown in the left graph has been set to be 24 by 24 kilometers in x and y, with spatial resolution of 19 meters or 100 times the wavelength of a GPS signal on the L1 band. These dimensions have been used in all simulations presented in this talk. The simulation of the signal propagation through the phase screen to the receiver is achieved by implementing a 2D split-step algorithm. The first part of the split-step method is to calculate the contribution of the phase screen to the change of the phase of the GPS signal. This is done by first converting the local tech irregularities on the screen into delays by using this formula. As the phase screen is not uniform, different parts of the screen will contribute differently to the delay of the signal's wavefront, resulting in diffraction. During this stage, it will be easier to describe the wavefront just below the screen in the spectral domain, decomposing the front into series of waves. Then each of those waves can be advanced separately from the screen to the receiver on the ground by introducing a propagation factor g. Finally, the wavefront is transformed back into the spatial domain using the inverse Fourier transform seen in the bottom equation. This produces a complex wave field on the ground that has been diffracted by the phase screen above. Any scintillation measurements, such as S4, can then be calculated using this field. So how does the two models tie in together in the overall method of the simulation? Given that we have simulated an ionospheric irregularity using real GPS measurements to set the model parameters, we can now obtain the complex wave field of a propagating GPS signal on the ground. According to the method plan, the final stage of the simulation is the calibration of the model parameters. This will be done by comparing the results from the simulation to real S4 measurements from the Yacamarca Observatory. Using the real part of the simulated waveform on the ground, we can calculate the S4 across the entire field. This will produce a time series of S4 values that can be used in the calibration of the models. So what are the parameters that affect the simulation? The table shown on this slide lists the parameters that need to be set in the initialization of the models. The table is divided into two sections, one for each model used in the simulation design. The irregularity phase screen requires information on the irregularity strength, delta n, which will be derived from the DTEC measurements from a GPS satellite, as well as the spectral index and the outer scale. The parameters that affect the propagation model are the height of the phase screen, which is set to 300 kilometers, the number of phase screens, currently set to 1, the size of the phase screen, which has been set to 24 by 24 kilometers, and lastly the spatial sampling of the screen, set to 19 meters or 100 times the wavelength of a GPS signal on the L1 frequency. The bolded parameters are the ones that the calibration stage will analyze. As can be seen, at this stage of the research, only the irregularity model is being calibrated. This will be expanded in the future. Parameters that are currently unspecified by the models are the thickness of the layer, the drift velocity, and the satellite motion across the sky. This will be included in future stages of the research. Before proceeding to run long simulations to optimize the irregularity parameters, it is important to analyze the sensitivity of the models to different values of its parameters. On this slide, each parameter of the irregularity was varied, while the other two were kept constant. This allowed to analyze the individual contributions of the parameters towards the S4 index calculated on the ground. The parameters' constant values are presented in this table. The sensitivity graphs on the top and the bottom left show that the simulated S4 reduces as both the outer scale and the spectral index increase. This is expected as both parameters control the steepness of the power law model. The effect of changing the irregularity strength on the S4 values seen in the right plot also behaves as expected. As the DTEC values recorded by the satellite increases, so does the calculated S4 value. It is interesting to note that according to the right plot, a DTEC of 5 times to the power of 15 produces a scintillation index of below 0.1. This is lower than initially expected, and its effects on the results will be discussed in the next slides of the presentation. Although descriptive, these graphs cannot show which parameter is more dominant towards the final S4 value compared to the other parameters. The next slide will address this question. This dominance can be analyzed by varying multiple parameters simultaneously and observing the resultant S4 at the ground. The graphs on the slide are 2D color plots, where the axes represent two of the model's parameters while keeping the third constant. The color signifies the S4 across the wave field on the ground. From the top graph, it can be seen that the spectral index dominates the values of the outer scale in terms of the resultant S4. Even for outer scales of between 200 and 400 kilometers, the S4 values start to reduce significantly for spectral indices above 3. The reverse is also true. Spectral indices of below 2 can preserve a higher S4 even if the outer scale is above 600 meters. The bottom two graphs show that the irregularity strength parameter dominates both the spectral index and the outer scale, specifically in the lower regions of the DTEC at below 0.4 TeC units. This can become a problem if the irregularity strength uses DTEC measurements from a GPS receiver. At the zero crossing of the DTEC measurement, i.e. when the DTEC values change sign from positive to a negative or vice versa, the receiver can record lower electron content, for instance below 0.1 TeC units, reducing the S4 values significantly. This will be shown and discussed further in the results section of the presentation. After the sensitivity of the irregularity model was analyzed, now is the time to show the results from a full simulation run for a specific case. The first step is to initialize the simulation. This will be driven by the observations and measurements obtained from the Yacamarca Observatory. The simulation will run for 1 hour between 0:15 hours and 1:15 hours UTC on the 24th of September 2014. The DTEC and S4 measurements for the irregularity model and calibration stages will be obtained from the PRN-29 GPS satellite. The reason behind this choice is that the PRN-29 satellite is close to its zenith in the sky during the observed ionospheric disturbance. This can be seen in the top graph shown on this slide. The strength of the irregularity, delta n, will be specified by the 15-second DTEC measurements from the satellite. These values will then be interpolated before the simulation to 1 Hz sampling frequency, so that the final S4 from the simulation can be calculated using a mean value over 60 samples at every minute. The input DTEC measurements and the interpolated input to the simulation can be seen in the bottom graphs, depicted in blue and red respectively. The optimization parameter space is also specified at the beginning of the simulation. For this particular case, the spectral index will range from 2 to 5 in steps of 1, and the outer scale from 200 meters to 1 kilometer in steps of 100 meters. The calibration will be achieved by calculating the root mean square error between the simulated and the measured S4 from the satellite. Similarly to the model sensitivity analysis, a color map will be used to show the calibration of the parameter space. The horizontal axis is the spectral index and the vertical axis is the outer scale. The color signifies the RMS error between the simulated S4 and the GPS measurements. It can be seen from the figure that as both the spectral index and the outer scale become higher, the error increases rapidly. It can also be observed a narrow section in which the parameters configurations achieves the lowest RMSE. It is denoted by a red line in the blue region of the color plot. The two configurations that produce the most accurate representation of the irregularity are spectral index of 2 and 3 and outer scales of 300 and 200 meters respectively. However, even the lowest RMSE is still 0.07, which is around 55% of the average scintillation index measured by the receiver. This will require the analysis of the time series of the simulated S4 in order to assess the reason behind this error. On this slide, you can see two graphs of the simulated S4 as time series for the two configurations with the lowest RMSE, shown in blue, referenced against the measurements from the receiver, shown in red. It is evident that the simulated S4 has a much higher frequency content than the GPS measurements. Moreover, the simulated S4 in both groups is almost identical, with only small difference in amplitude. The only parameter that can affect both simulations in this way is the input DTEC. As it was shown in the sensitivity study, a change in the magnitude of the irregularity strength can significantly alter the S4 values, diminishing the effect of the other two model parameters. The next slide will provide further evidence to support that the DTEC is the main contributor to the high frequency content found in the simulated S4. The figures on this slide present the simulated S4, shown in red, against the input DTEC, shown in blue, obtained from the PRN-29 satellite. It can be clearly seen that the simulated scintillation index closely follows the behavior of the DTEC measurements. This is an important finding as it shows that for the development of the models and the research, a better description of the locally changing electron content could be required. The main question left after the initial development of the irregularity and propagation models presented in this talk is, can this methodology be transferred to characterizing wideband communication channels? Assuming that the calibration can narrow down the values of the required parameters and that the input data from real observations is conditioned appropriately, can the phase screen and propagation model estimate coherency times and coherency bandwidths well? From the perspective of the current stage of our models, this will require the implementation of ray tracing algorithms as well as the inclusion of wideband RF data in order to test the applicability of our models to wideband channel simulation. Thank you for your time.